So we've just finished talking about voltaic cells, and there have been some definitions like electrode, electrolyte. We're about to experience some more words that get muddled up, like electrolysis, electrolytic cell, of the electrolyte in the electrochemistry unit. And they all sound very similar, and so you need to write yourself a list to sort them out. Right. So electrolysis. Electrolysis is providing electricity to force a non-spontaneous redox reaction to occur. So your battery in your phone is working spontaneously. It's producing a charge which runs your apps. It produces a charge which runs your Wi-Fi. It produces a charge which... You got it? This is when you plug in your phone and you're recharging it. Okay? So I'm forcing that spontaneous reaction to reverse itself. So do you remember when we were talking about the voltaic cell? And actually this is even before the voltaic cell. We were talking about how you go to the cafeteria and somebody is given or gains 2 muffins, and the cafeteria lost 2 muffins, and that had to balance. Do you remember that? That's quite spontaneous. The student wants to eat, so it is happy to gain 2 muffins. The cafeteria wants to make money, so they're happy to lose those 2 muffins. Spontaneously, that happens. Right? If I went up to the cafeteria and went, "How very dare you? You must return your muffins." The student's not very happy. Cafeteria is not very happy. Cafeteria's just lost money. But I'm forcing that student to give up its muffins back to the cafeteria. I'm forcing the cafeteria workers to take those muffins and put them back on their shelf. Okay? That's what electrolysis is. It's forcing those electrons to go in the other direction. So up until now, our reactions have been about the strongest oxidizing agent and the strongest reducing agent in our voltaic cells, and it was always spontaneous. Right? Don't knock my tea over. Okay, it was always spontaneous, and now what I'm doing, I'm going to use a lot of colors today. Now what I'm doing is this reaction, I'm forcing those electrons to go back upstream. So I'm, if this has happened, I'm using up all of this stuff. And eventually the stuff's all used up, my battery dies. So recharging it replaces that stuff. But I've got to get the salmons to go upstream again. Okay? Make sense? Everybody get where we're going? Okay. Okay, so electrolytic cells have 2 electrodes. Same or different as the voltaic cell so far? Come on, guys. Voltaic cell? You know the voltaic cell that we just did? All that work you just learned? Everything you know? Does it have 2 electrodes?
Yeah.
No, same thing. Does the voltaic cell have an electrolyte? There's always 2 electrolytes in a voltaic cell. In an electrolytic cell, I can have 1 or 2 electrolytes. Okay, so that's a little different. 1 or 2, whereas the voltaic cell was always 2. Electrolytic cell needs a power source, like a battery or something, to make it go. Did I need a battery or anything to make the ones that you did in class go? No. So this is very different as well. This is the same. So just as a water pump pumps the water uphill, a power source or a battery or a generator or whatever can pump electrons against the spontaneity and up that hill. Okay? An electrolytic cell is the reverse of a voltaic cell. So reactants, voltaic cell, products and energy. Whereas if I have to put energy into it, I actually can reverse it, get my reactants back again. That's called an electrolytic cell. Have you seen this concept before? Yeah, where did you see it? Delta H. Right? If it's an exothermic reaction, I could put that energy back in and make it endothermic. Formation, decomposition. Do you remember that? Same concept. Okay. You'll see it a third time as well, by the way, by the time you're finished. Okay, so for example, we have here silver and copper ion silver, and the voltage should be 0.76 volts. Let's just do this like yesterday. Okay, so ignore the double arrow because we didn't have those yesterday. And I've got silver ions and copper. I've got a silver copper cell. What did we do? Listed our species, right? Silver and silver ion and copper ion and copper is the cell. And I went and found my strongest oxidizing agent and found my strongest reducing agent. So this is my strongest reducing agent. This is my strongest oxidizing agent in your data booklet. And the strongest oxidizing agent was indeed above the strongest reducing agent, and it indeed was a spontaneous reaction. No different, just like yesterday. Ag1 plus 1 electron goes to Ag. Cu goes to Cu, 2 plus 2 electrons. Right? Times that one by 2, and I get 2 Ag pluses, and a Cu goes to 2 Ags and a Cu2 plus. And while we're here, we might as well correct these big 2's here. Okay? And we even beefed it up and we found the voltage. What's the voltage of Ag?
0.80.
0.80. And the voltage of, what does it look like exactly on the data booklet? I want to top minus bottom.
It would be 0.34 positive from Cu2 plus 2 electrons to
Okay?
Cs.
So exactly like the data booklet. Exactly like the data booklet. Subtract them if it's cathode minus anode, exactly like the data booklet, and I get 0.46 volts, exactly what's written there. Positive, and I put the positive in because it means something now to us, meaning it's spontaneous. It gives out, it produces. Positive 0.46 volts. Everybody fine with all that? That's yesterday. Okay, last week. I shouldn't have been saying anything new here. All right, so that's the voltaic cell. Electrolytic cells, though, are saying, oh no, I've used up all my copper. Remember the copper stick? What would be happening to the copper stick here? It'd be getting smaller and smaller and smaller in mass. And eventually the battery dies. No copper stick left. Well, or it's actually, there is some left, but it's no longer covered in the solution or something. So I can hook it up to a power source and I can force the electrons to go in the opposite direction. Remember? So this is like the cafeteria. Oh no, student, got to return it. I'm forcing them to go in the other direction, restocking the shelves, remaking my copper and remaking my copper ion. So over here, I'm going to look at my species again. So let's say no longer voltaic, students, it's now electrolytic. Oh no! What do? Well, you start the same place. I'm going to list my species. So I've got, there. Species-wise, I have Ag, I've got Ag+, I've got Cu2+, and I've got Cu. Now here's where it's different. Because it's electrolytic, I'm wanting the waterfall to go uphill. So I'm looking for this thing, uphill, that thing. So remember how you said in like chapter or whatever it was before this, that this would be spontaneous? I'm wanting the final arrow to write non-spontaneous, because it's an electrolytic cell. So I'm looking for those two. And if you look in your data booklet, you will see that this one is Ag1+, and this is copper. In that, if I want the waterfall to be uphill, if I want it to be non-spontaneous. Okay? So my Ag1+ is reacting, and my Cu is reacting. Well, Ag is going to gain an electron to become silver metal. Copper will be becoming copper 2+ and losing those 2 electrons. What the other way.
Yeah, the
Sorry.
AGS2
Sorry. Oh dear. This is really proud. Cu2 plus, right? And Ag. Oh dear. Okay, back again. So this is Cu2 plus, this is Ag, and so therefore this Cu2 plus will be gaining those 2 electrons back and becoming that copper original. And the Ag will be deconstructing into Ag plus and losing that 1 electron. And if I write this net reaction, I would indeed be writing copper 2 plus 2 Ags goes to 2 Ag ions and a copper, and over top of that, it's non-spontaneous. Non-spontaneous. So electrolytic cell, voltaic cell. Okay? Now if this waterfall gave out 0.46 volts, in order to reverse it, how much voltage do you think is needed to be put back in? 0.46. The same amount. Right? Exactly like on my delta H's, were the same amount but reverse. Same thing.
So do you still write it on the right side though, as positive?
Well, we don't normally write it in the thing. I was just trying to tie it to unit 1 here. We normally write it beside it. So like in delta H notation as opposed to within the balanced chemical equation. So here I'm going to write that my E naught delta, so the change in electrical potential energy at standard temperature conditions, would be negative 0.46 volts. The exact opposite. Why? Because we spent a long time yesterday learning that voltage is the distance, the difference. Right? My son's 3 years apart. Your family, whatever, right? So 3 years apart, whether you're looking at it from my youngest son to the oldest son, or the oldest son to the youngest son. It's just whether I subtract 3 or add 3. It's the same thing. This is giving out. So to reverse it, I have to put in the exact same number, though.
So is it always going to, the E naught negative is going to be negative when it's non-spontaneous?
Right.
Okay.
All our other voltages, when we were talking about voltaic cell, happen to be positive. It always worked out that way. Why? Because they're voltaic. As soon as you know it's electrolytic, it must be negative. So a great question would be, this is the voltage of the cathode, this is the voltage of the anode, cathode minus anode. What is your potential energy? And is this a voltaic or electrolytic cell? Well, if the voltage ends up being negative, it's electrolytic. Happy? Okay, so moving on. Oh yes, remember those notes you did on cells? Dry cell, primary cell, secondary cell. The secondary cell is electrolytic cell. Okay, so for example, this nickel cadmium cell that you did a bit of work reading about, this is what we're talking about now. Okay, so I've written a little summary here about the difference between the voltaic cells and electrolytic cells. Although when I was going through this in the morning period, I was like, I can't really remember what I wrote, why I wrote that. But anyway, here we go. So voltaic cells always have positive voltage. Electrolytic cells always have negative voltage. Okay? The positive voltage means that voltage is given off. There is energy. Energy taken in. I don't see. I don't even know why I wrote that. Scratch it out. I don't know. It doesn't make sense. And it is the exact opposite of the electrolytic cell. That is true. Yeah, scratch this. I don't like that. But it is positive energy. The electrolytic cells have negative voltage because it's a negative deficit. It has been put out by that much voltage. You need to replace it. So it needs to be added to react. And the power source adds to it. Okie dokie. Okie dokie. So this is actually in your textbook, and I just thought it was great to be able to write all over it. So I photocopied it for you and put it in your package so you could write all over this example. We're going to do voltaic cell first, same as last couple weeks. Then we'll do electrolytic cell, we'll compare the differences. Okay, and you have a comparison chart that we will fill in here to get it all sorted in our head. Okay, so zinc copper cell here. What did we do? What's the first thing we do? List our species. So I've got zinc and zinc ion, and I've got copper ion and copper. And because it's spontaneous, we're looking at our strongest and strongest, and so therefore I find out that my zinc is my strongest reducing agent, my copper is my strongest oxidizing agent, copper ion. That's frustrating. And my zinc, just copying from the data booklet, will become zinc 2 plus and 2 electrons, and my copper 2 plus will become copper and, what? My copper 2 plus will gain the 2 electrons and become copper. The voltage on this is, what's the voltage of zinc and the voltage of copper?
Is -0.76.
Negative 0.76, and copper on the data booklet.
0.34 positive.
Pardon me?
0.34 positive.
And so cathode, oh, this is cathode minus anode, or top minus bottom. And so the cathode minus the anode is, what? That doesn't work out. Hold on, let me look it up myself. Copper is positive, 0.34, zinc is negative. Oh, that's why. It does work out, I just wrote it down wrong. So cathode minus the anode, which happens to be negative. And so therefore I get, this is much better, 1.10 volts positive. Everybody okay with that?
So would you want us to write it though with the E notch, the change in E notch?
Sure. This is losing electrons, oxidation at the anode, which is why that's titled anode. This is gaining electrons, which is reduction at the cathode, which is why the copper is titled 12, is given the title the cathode. And I'm just going to erase that and write it over here. Cathode minus anode is positive 0.34 minus negative 0.76, which equals positive 1.10 volts. E naught delta, if you like. Okay. Everybody okay with that? Everybody understand how I identified anode and cathode? And so the electrons flow from the anode to the cathode, right? So here are the electrons flowing from the anode to the cathode. And anions are attracted to the anode through the salt bridge. These SO4 2 minuses will be going through this invisible salt bridge because the photocopy didn't photocopy it. Is yours? Do you have a salt bridge on yours? Not really. You can see the little plugs here. There was one. It's just a bad photocopy job. And so because these SO4 2 minuses are surrounded by anodes, or by anions, the anode is then negatively charged. Okay? The anode is negatively charged. And because the cations are traveling to the cathode, the zinc 2 plus and the Cu 2 pluses will be hanging out here. The cathode will be positively charged. And I think that's everything we know about a voltaic cell. Yes? So just take I know, I made a mistake on your package. I'll correct that in a second. Just take 2 minutes. I'll correct that at the end of the class, okay? Take 2 minutes and fill in just the voltaic cell section of this table with the couple people around you.
Isn't the anode positive? Oh. I thought it was just an overall. Right.
Anode is negative, cathode is positive for voltaic cells. Just trust me. I'll talk about it in detail after the video's over. How about? Okay. Okay. So spontaneously, you've got to build up vessel 42 minus at this post, and that's why it's negatively charged. Or you could say the electrons are flying out of here. So if I stop it, stop the wire, the electrons are coming out from here. So this is the source of electrons, so it's negative. Not negative as in, you've got to stop thinking about negative as in a negative line on a number line. Okay? Think of it as electrons. This is where the electrons are coming from. This is where the cations are, so it's positive. Okay? All right, so everybody okay with this order? And the electrons flow from the anode to the cathode, the direction of the ion flow to the anode, to the cathode, spontaneous, positive, and it supplies energy. Okay, so now we're going to start an understanding of electrolytic cells, or we're going to continue our understanding of electrolytic cells. The first thing I need you to absolutely sort out is that Leoa still says Gurk. Okay? Leoa still says Gurk. That does not change. That's so important for you to grasp because that makes or breaks the rest of the logic. Yes, girls?
We were wondering if you had a Bunsen burner.
I do. Do you just need one?
Yes, please.
Okay. I'm going to give you two just in case this one breaks or like it doesn't work or something. And do you have matches? Does your teacher have
Yes.
matches? Okay.
Thank you.
You're welcome. Okay, so that's really important. This Leoa still says Gurk. Now I'm going to rub this out so I can scroll up and do the diagram, but you are going to flip between the two. Okay? So back up at these pictures. Right there. Okay. I have this system. You can see it has a battery here. And as soon as you see a battery, you know it's electrolytic. When you see nothing or a voltmeter, you know it's voltaic. So that's how you tell the difference between the two pictures as to which is voltaic and which is electrolytic. As soon as I see a power source, a battery, a generator, or it might just say power source, you know electrolytic. Okay? And because it's electrolytic, you know I'm pumping the electrons up the waterfall. So I still have zinc, and I still have zinc ion, and I still have copper ions, and I still have copper. But I'm looking for the combination that's going to give me a non-spontaneous reaction, because that's what this is. So I'm looking for the two that make the waterfall up the hill, make that statement true. Okay? So you look it up in your data booklet, and you should see that copper should be going here, no, here, and zinc ion is here. And so therefore, I know I'm going to start with zinc ion, and I know I'm going to start with copper. I'm going to go this way, and I'm going to go that way, reading the data booklet. So the zinc ion is going to be gaining 2 electrons and becoming zinc. And the copper is going to be becoming copper 2+ and losing its 2 electrons. And therefore, I have Zn2+ plus Cu goes to Cu2+ plus Zn, and that's non-spontaneous. That's what I was after. That's the whole reason I did those two and not the other two. So I'm not picking my strongest and strongest anymore. I'll say that again. I am not picking my strongest and strongest anymore. Because it's not spontaneous. I am picking the waterfall goes up.
So wouldn't it just be the weakest of each?
It's kind of like saying the weakest and the weakest, yeah. Although I don't really want to say that because there's probably water somewhere in here, and the water might be one of the weakest, so I'm trying to avoid saying that, but yes, that's basically what you're doing. Okay? Everybody all right so far? This is gaining electrons or losing electrons.
Gain.
So it is Gurk. This is losing electrons, so it's Leoa. And we learned that Leoa still says Gurk. Right? I just finished saying that's vital. So over here, we said, oh, Gurk, this reaction, copper cathode, Leoa anode at the zinc section, so anode at the zinc section. Here I'm saying Gurk at the zinc section. So the cathode has just become the zinc section. See how the cathode and anode switch spots? Because the other one is being gurked. Okay? If there was such a word. And the anode is a loss of electrons, and it's the copper system, half cell, that's losing electrons. Okay? Okay, so Leoa still says Gurk. So we still have the anode and the cathode labeled as such, but the metal has switched its label. Okay? The electrons still flow from the anode to the cathode. So the electrons are going in the other direction. Oh yeah, we said that, right? We said we were trying to pump them backwards. Remember? So that makes sense. They're pumping backwards and they're still flowing from the anode to the cathode. So actually it's something else we can put on your little table now. Not only does Leoa says Gurk still apply, but we know that the electrons still flow from the anode to the cathode. Just like the voltaic cell does. Okay? And continuing with our logic, oops, the zinc 2 plus over here will have depleted, right, disappeared, because I'm using it up. And here I'm making it, so this is now building up in mass. The zinc ions are going here to collect their 2 electrons and become more zinc. Agreed? So the cations are still going to the cathode. So we can fix that on our table. The cations are still going to the cathode. Maybe I should put this on the same sheet next year, hey? And therefore the anions will still be going to the anode. Through the salt bridge. The copper is breaking up into copper 2 plus ions, so this has become more and more blue, this solution. And those 2 electrons are going to be going this way. Actually, it's not necessarily true, because then they're going to travel, those cations will travel to the cathode. So the whole thing will become more blue. Anyway, but the copper is replacing the battery's electrons, or completing the circuit. You see that? What else is there to fill in on that table that we haven't filled in yet? The charge.
Of the anode and cathode.
The cathode is now negative, so they switch their charges. The cathode is now negative because the electrons are going here. It's different. It's opposite.
So it's where the electrons are falling.
Yeah, I'll explain why in a minute. Maybe you'll see it a bit better. And the anode is positive because it's where the cations are going, and so that area will be surrounded. Oh, what? No, the anode is positive because I think because it's producing the Cu2 plus ions. Okay. Anything else to fill in on that chart, the comparison chart? That's it? Okay, so here's your voltaic cell, here's your electrolytic cell. This is a battery. This is recharging. This is spontaneous, this is non-spontaneous. I think that's in your list too. Non-spontaneous, negative voltage, and something else.
If it requires energy.
If it requires energy, so this one requires. Now, didn't I just say this is a battery?
Yeah.
So this is this box. That box is this. So if I disconnect this wire for a second, right? And I take these electrons that are firing out of here, and I take them and I take them and I plug them in here. That's the same thing as electrons firing out of our battery. Our electrons are firing out of our battery and going to this post. You see that? And that's why this is negative. That's why we had to switch the cathode and anode to be negative at one and positive on the other. Because the negative electrons are being produced from here and being piled into here. Do you get it? And likewise, this positive wire would then be hooked up to that positive post. And that's why it's positive, because the battery has told it it's positive, because I'm pumping them uphill. Okay? You with me? Okay. So, this says, highlight the above chart to find out what's different between electrolytic and voltaic cells. Oh, I forgot to do the voltage on that last one. Can you, on the last one, I've just rubbed it out, But can you take your cathode minus your anode, please? Yeah, but prove it to yourself. So take your cathode value. What's your cathode again? The what? The zinc. So take your zinc voltage, cathode, minus your anode, which is your copper voltage. Do it in your calculator as if you didn't even see the first half done. And you should get negative 1.1, which of course you would have expected because you did it already 5 minutes ago. But prove to yourself if you only had electrolytic cell, it's still cathode minus anode.
So could you definitely?
But it's not top minus bottom anymore. So the waterfall went like this. This is your cathode. This is your anode. So it's now bottom minus top. But some students prefer to still go top minus bottom, know it's electrolytic, so they switch the sign. That's okay. Okay? It kind of just depends on how they ask the question. If it's a drawing and they've said the cathode is, the anode is, it might be easier to just go cathode minus anode. But if it's looking up in your data booklet, it might be easier to go top minus bottom and then know it's electrolytic, so then you make it from positive to negative sign. Get it? Okay. So for the camera's purposes, this is the list that matches that. Oh, do you know what? That's skills. Oh no, it doesn't quite do that. Almost. Anyway, I'll just zoom like this. Okay? You can pause it and see it. And then we're going to highlight the chart as to what the differences are. You should find 5, I think, off the top of my head. And then you're going to do these practice problems in your data book in order to, or in your textbook, I mean, in order to make sure you get this stuff a little more. Okie dokie. Tomorrow we're going to do a bit more practice. And then I have a lab for you.